Hello, this is Jack Baker. In this section, I'm going to talk about reliability modeling under random vibrations, and specifically with the objective of modeling fatigue failure. From the textbook, this is going to be sections 11.7 to 11.8. That general section of the book talks about fatigue failure with a number of different models. I'm going to give you a sampling here of a couple particular models that are quite popular, and with focus on kind of tying them back to the properties of stochastic processes that we studied earlier in the class. Okay, so let's think a little bit about failures in general and how we might model those mathematically as they relate to treating the x of t as a stochastic process around structural response. So let's think about, we'll talk about kind of stress in a material here right now. So this would be kind of a response parameter. You could think about similar response parameters for of other types like displacements or forces, but for the fatigue failure problem we'll talk about in this section, stress is usually the parameter we're thinking about. So we could think about a few different properties of x of t. So we might be interested in the maximum value of x of t. So let's say there was a service life of the structure from 0 to big T, and we're interested in what's the probability that this x of t process could, say, exceed a yield stress. And so for that type of thing, we would want to think about the extreme values of the process, and we could think about trying to find the probability of exceeding x yield using the upcrossing rates that we discussed previously. We can also think about something we might call like a serviceability failure, to say there's some allowable x and we're allowed to exceed it a little bit, but not too often. So we might say, no more than 2% of the time could we get above some level of response. And so it's not necessarily a safety problem to be exceeding that, but it would be something we'd like to avoid in general. Again, we can think about upcrossing rates from that. The fatigue failure, the third one, is really going to be the one we'll focus on here. And this one's a little bit different because rather than thinking about just an extreme of the process, we're going to think about an accumulation of damage. So any particular cycle of loading on the structure is not necessarily going to cause a failure or a non-failure, but it's going to cause some level of damage that's going to accumulate over time, and we want to know what's the likelihood of accumulating enough damage that we get a failure, say, over some service life of the structure, or how might we specify a service life to have a reasonably high probability that we wouldn't accumulate excessive damage over that service life. So let's talk about that one. And what I'll do is I'll introduce kind of a high-level approach for how we think about this accumulation of damage, and then we'll dig in a little bit and try to relate that to properties of stochastic processes, as we've discussed earlier in the class. Okay, so the easy way to think about accumulation of damage is to think about a case where we've got constant amplitude loading. So we could think about our stochastic process, or just a loading process in general, as being time and x as a function of time. And we could think about even, say, a harmonic load, but it's not too critical what the form of it is. The key is that the loading is constant in amplitude for each cycle. So we could call this S, let's say minus S being the thresholds that we hit on each cycle of loading. And then we want to say how many cycles of loading does it take to get to a failure, depending on how big that amplitude S is. And so NF would be the number of cycles to fail. That would be a random variable in general, but what we often get if we repeat this kind of constant amplitude loading for a variety of levels of S, and then plot that versus the number of cycles to get a failure, is we'll get a figure that looks like this. So on the x-axis we'll have log NF and log S. And we will get, if we plot this in a log-log scale, we'll get a linear relationship. Make that a little more linear. Okay, and so the form of that equation, if it's linear in log-log space, is that NF is equal to 1 over C S to the minus B. Okay, So the C and the B are constants. And then if you take logarithms of both sides, you get a linear function. So that's why it's linear in log scale. So that we've got S versus N here. And so this type of figure gets called an SN curve. And we're typically using this for high cycle fatigue. And high cycle fatigue, that's a domain where the number of cycles to failure is something like 10 to the 4th to 10 to the 7th. So we're talking about kind of thousands to millions of cycles. So there's a low cycle fatigue where you go below 10 to the 4th approximately, and then there's an ultra low cycle fatigue where you're thinking about just dozens of cycles at very high stress levels. And so in those low cycle and ultra low cycle domains, this type of relationship will break down. But in that high cycle fatigue range, you often see this log linear relationship. And further, we can say typically that B exponent is approximately equal to 2 to 8. So this is saying that so say if B is 2, if you double the stress amplitude in that top figure, that you're going to reduce the number of cycles to failure by a factor of 4. And if B is 8, if you double the stress amplitude, you're going to reduce the number of cycles by a factor of 64. So it's indicating kind of how fast the failure onset happens, more quickly as the stress amplitude gets bigger. And that range in B is dependent on the material you're looking at. So some materials are going to be more susceptible to high amplitudes than others. So each material will have its own B coefficient. Okay. So here's an example. So this was an SN curve I took from some documents. You can see SN curve up here, and it's for a particular type of material. Right? So this is brittle aluminum, some additional specifications over there on the right. So the horizontal axis, it says life in number of cycles. So this is our NF. And on the vertical axis is stress in megapascals. So this is our S. And so you can see this plot ranges from 1 cycle up to 10 to the 7th cycles. And it's the 10 to the 4th to the 10 to the 7th range that's the high cycle fatigue. And you can see out in this domain here, we've got approximately a linear relationship. In the plot, and you can see this plot is in log scale in the horizontal axis. So each each label we move over, we're going up by a factor of 10 in the number of cycles. The vertical axis is not in log scale here, but because the range of stress is not so big, the linear versus log scale doesn't look dramatically different. This would look even a little more linear if we put it in the vertical log scale. Okay, and so the n equals 1 over c s to the minus b function you could fit out in that range. And then over on the left side of the figure would be the other fatigue failure domains, and you can see the slope of the curve changes a little bit from place to place there. Okay, so that's what an SN curve looks like. And then so our question is a couple things. So we've got to think about how we might actually calibrate something like this, and we need to think about what does this mean for kind of stochastic loading. And of more interest for our class here today is that we need to think about, well, what if the loading is variable in amplitude, right? So the real world is not giving our materials constant amplitude loading. There's going to be some large amplitude cycles of loading and some small amplitude cycles of loading. So how do we take this type of concept and extend it to this variable amplitude loading case? So let's dig into that a little bit. Okay, so we want to think about using the same concept, but we don't want to specify each cycle of loading's amplitude. We want to think about some sort of a stochastic description here. And so Miner's rule is by far the most popular way for doing this. Miner's rule is underlying most building codes in the world, some aspect of the fatigue failure and things like that. So let's make a note. This is used in almost every design code worldwide. So here's the idea. We're going to say there's a variety of different stress magnitudes, and each time we go through a cycle that, or through a cycle of loading, that depending on the magnitude of that loading, we're going to get kind of NI effective cycles added to our loading, and we have some sort of total budget of the number of cycles we can handle. That's going to be big NI, and if we had a constant stress amplitude SI, we could figure out how many cycles that would take. But here now, when we have these variable cycles of loading, we're just going to have a budget of total cycles, and we're going to accumulate against that budget until we get to a failure. So the equation we need, I guess let's write that down. So we're going to have the sum of these cycles Ni for each, this is kind of the number of cycles we lose out of magnitude SI versus relative to Ni, our total budget. And we're going to sum these I equals 1 to k cycles of loading until we get up to C. And C is going to be our total budget, so we'll say kind of typically C equals 1. So then we can interpret this Ni, small ni divided by large Ni, as kind of the fraction of the fatigue life consumed by cycles at amplitude SI. Okay. So if we rearrange a little bit, we're going to call the damage, and so we've got this kind of damage that we're accumulating for each cycle. And what we'll say is that the damage we accumulate for each cycle is going to be the stress amplitude SI raised to some power B, and then we've got a coefficient out front to kind of indicate how fast that damage is accumulating. And the B exponent will again control the larger amplitudes, how much more damaging those are in each cycle. Okay, so we'll have that damage per cycle, and then we're going to add up the damage per cycle over all the different cycles with this summation. Let's think. So we got this linear damage accumulation where we're just adding up the damage per cycle. And this delta is going to be our total damage. So again, we'll say we'll have failure when this big delta in total damage is equal to 1. And then on the other side here, we're adding up this damage per cycle. And remember, we were just talking about that if we had constant cycles of loading, so we can think about that case, so that we're going to add this thing up until it's equal to 1, and kind of rearranging the equations from a couple slides ago, we can write number of cycles to failure times C times SI to the power B. So that would be the case if the SI is constant. And I'm taking this equation from just a rearrangement of 3 slides back, where we said 1 over C SI to the minus SI to the power minus B is equal to NF. If I back up to slide 12.3, right, that was our equation for SN curve. So we can get that by just dividing both sides in this mid-page equation by C SI to the B. So that's the constant stress loading condition. But now we don't have a constant SI, the generalization we're going to make. So we don't have a uniform accumulation of damage per cycle. So what we've got instead is we can make a plot of, say, the number of cycles versus delta. And so at each cycle, we're accumulating some amount of damage, DI. In some cycles, we accumulate more. In some cycles, we accumulate less. We're moving along. And then once we reach 1, we're going to call that failure. So we're going to be interested in kind of how many cycles does it take to get to a failure under this variable amplitude loading, and how long does it take to get to failure as well in time. So this would be, call this NF. And so this constant amplitude case is kind of in the neighborhood of what we're interested in, but not quite. So we can say, if we've got this stair-steppy equation, we could think about replacing that stair-step with a kind of a straight line and thinking about kind of on average, how are we accumulating damage? So let's replace the stair steps with a straight line, just thinking about the expected values. So we could say the expected value of the damage from a particular cycle is going to be the expected value of how much damage has been accumulated. So it's C SI to the power B. The constant C can come outside. But SI to the power B stays in the expectation because SI is unknown for a particular cycle. And then the expected value of delta, the total accumulated damage, at some instant of time or after some number of cycles, is going to be the sum over all the cycles that have happened of the expected value of DI. Okay. So now we've thought about the kind of the, with these formulas, we're going to be able to get at potentially the number of cycles to failure. And if we're interested in the time to failure, so let's call that TF. So I'd be interested in knowing, is my bridge girder going to last 30 years if it's getting cycled by cars passing over it, something like that? Well, I can figure that out by thinking about the number of cycles to failure, which is what we've been setting up our equations for. And then we got to say, well, how often do cycles happen? So that's going to be this F subscript C is going to be the rate of cycles. And where we're going with this is when we think about our stochastic processes, right, we could measure a cycle as the rate of that process upcrossing the mean. So every time it upcrosses its mean value, we'll call that a cycle that's passed. Okay. And this expected number of cycles to failure, we could think about that as approximately equal to 1 divided by the amount of damage or the fraction of damage we accumulate in each particular cycle. So that could be the C times the expected value of SI to the B. That's approximately equal because we took 1 divided by the expected value rather than the expected value of 1 divided by this thing. That's just going to be easier to compute this thing, but it's a kind of a reasonable approximation given the other assumptions we're going to handle here, or we're going to make here. Okay, so we've got this this formulation where the right-hand side, the rate of cycles we can come up with from our stochastic process model. SI is going to be some amplitudes we can figure out from random vibration theory. Let's write this down, I guess. So the expected value of SI to the B, we're going to need that in this above formula. So we need to figure that out, but we can do that using random vibration theory. As we'll talk about in just a second. And then C and B are just going to be constants, and we can calibrate those using the constant amplitude tests. So we can run some constant amplitude fatigue failure experiments, figure out what C and B are using that old SN curve. And then we need to figure out, well, depending on the variability of our stresses from cycle to cycle, what's the expected value of this SI raised to some exponent. Okay, so and we can think about that as basically the mean damage that's accumulated in each cycle, or it's proportional to it within those C and B constants. Okay, so let's think about how we're going to use random vibration theory to find this expected value term. Okay, so let's think about it loading again. We'll make it not constant in amplitude this time. So the realization of our process could look like x of t versus t. So it's coming down, up, down, up, and so on. Okay. So, as I said before, what we're going to do, we're going to call a cycle is going to be an upcrossing of the mean. So here we upcross once, then over here we upcross again, and upcross again, and upcross again. And let's just call this a mean zero process, so that my zero line here is the mean. Okay, so I don't need it to be mean zero. If it's a mean of something else, I could just count an upcrossing of that. But a lot of times for material stresses and things like that, when we go to positive and negative stresses, we could think about zero mean process. Okay, and so we've got kind of 4 cycles on the page if we've got 4 upcrossings. And then what we're going to say in terms of the amplitude of each cycle is we're going to take SI, that's the number we're interested in, and that's going to be the maximum value of x of t in any cycle. Or let me write that a little bit better. Let's call it cycle I. Okay. So in this first cycle, the maximum was up here, so we could call that S1. In the second cycle, the maximum is there, S2, S3, and S4. Okay. And then if we just think about the maximum, right, what we're doing is we're going to ignore any kind of local maxima that are not the maximum of the cycle. So for instance, here I've got this small maxima, so I'm going to ignore that one. That's neither a cycle nor a maximum stress that we're going to count in our calculations. Okay? So, and the reason for doing it this way is that this is pretty simple. And it actually works out pretty well empirically. So I'll say it agrees with experimental calibrations. So what I mean is that when we're trying to do experiments, loading materials and watching them fail, that these local maxima, like this point that was ignored, don't seem to contribute much, and they may not happen very often as well, right? So if it's a narrow band process, we don't get that many of these peaks relative to the crossings anyways. But it's and you can think about it with this SI to the B, when we have that exponent on there, it means that the large amplitudes are contributing disproportionately to damage relative to the small amplitudes. And so looking at just the maxima from each cycle is also a reasonable thing to do under that picture. Okay, so let's continue on. And so what we're interested in then is kind of what's the probability of this SI taking a particular value, the maximum value in the cycle taking a particular value. Because if we could figure out that probability distribution for SI, then we could figure out the expected value of SI to the B. Okay, and it turns out those upcrossing rates that we recently studied are going to be a nice tool for getting there. So let's write it down this way. So I'm going to say the probability that SI is greater than some value S. So in a particular cycle, we exceed S. Well, what we'll do is we'll compute the expected number of upcrossings of S divided by the expected number of upcrossings of the mean of X. Okay, so the idea would be if in some interval of time I had 10 upcrossings of the mean in my denominator, so that would mean I had 10 cycles on average. And in the numerator, I expected to see 2 upcrossings of S. So out of 10 cycles, I see 2 upcrossings. That means in any particular cycle, I have a 2 out of 10 probability that I'm going to exceed that threshold, small s. Okay, so that's kind of an easy way to get to these probabilities. There's one question, kind of relates to my picture on the previous slide, is what happens if there's or let's just, I need to write that down. We'll just say, what about if there's 2 upcrossings in a cycle? All right, so what if in that previous slide, when we had this ignored point right there, you could say, well, what if in this particular cycle, what if I upcrossed some threshold twice because I went up and down and back up again? So that's potentially a problem, but it's not numerically going to be a big deal under 2 conditions. So this is, let's say it's not a numerical issue if under one or the other of these 2 conditions. If S is large, so that we don't get that many upcrossings to begin with, and so we have a relatively low probability of an upcrossing, then the probability of getting above it twice within a particular cycle is really rare. So as you're closer to the mean, you might get larger chances of having 2 upcrossings. But if you're looking at high amplitudes, that's not a problem. And under a lot of circumstances, it's kind of the larger amplitudes that are what we're going to be worried about, because the very low amplitude is not going to be kind of causing damage to the material. The other situation where this isn't a problem is if X of t is narrow band. Remember we talked about in the upcrossing section that if X of t is narrow band, then the number of peaks is about the same as the number of, it's about the same as the number of mean crossings, and so we don't have any of those local peaks to worry about. So under either one of those circumstances, we're fine. The large amplitudes is typically a situation we're interested in for damage accumulation, and then the X of t being narrow band a lot of times is a situation that's a reasonable approximation because we're thinking about stresses induced by a structural response, and the structural response oftentimes looks pseudo-narrowband. Because of that frequency response function only paying attention to a particular range of frequencies. So there's some reasons to suspect that this might be reasonable assumptions. So we'll continue on with that as our treatment of this. Okay, so these expected numbers of crossings, we can compute those as crossing rates. So the numerator is going to be the rate of up crossings of S multiplied by T, the time interval that we're studying here. And the denominator is going to be the rate of up crossings of the mean, also multiplied by that time interval. And so those time intervals don't matter, right? It's really just the ratio of rates rather than the ratio of numbers that, or the ratio of rates and the ratio of numbers of up crossings are going to be equivalent. So we can delete those or cancel them out. So we have the rate of up crossings of S divided by the rate of up crossings of the mean. Okay, so that's the probability of an exceedance of S. If we want to look at this cumulative distribution function for SI, so the probability that SI is less than small s, that's just going to be 1 minus the probability we found above. And if we want to find the probability density function for SI, right, that's just the derivative of this cumulative distribution function, which is 1 minus the term we found above. So we won't bother kind of spelling these things out just yet. But let's note that that's going to be useful to have the PDF, because ultimately what I'm interested in is the expected value of this SI to the power B. Right, so I need this B exponent in there, not just the mean value of SI. And so just using the definition of an expectation, I can talk about finding the expected value of SI to the B. So we'll just use a dummy variable y in place of SI. So we'll call that y to the B. And then we need the probability density function for SI evaluated at y. And then we're just going to integrate over all y's. And then since, these SI's are, and we're just going to look at positive stresses here. So let's just call this 0 to infinity. And I guess I kind of went by that quickly. In our figure, we just were highlighting the positive stresses. There's a couple ways we could handle this, right? If we need to think about accumulation of stress in one particular direction, say accumulation of tensile stresses accumulating damage, then we can just call that direction positive. If the absolute value of the stress is interesting, then we can think about taking the positives and the negatives. There's just an adjustment we would make there, but conceptually it wouldn't be dramatically different. Okay, so if we know the PDF for SI, then we can find the expected value for SI to the power B using this equation at the bottom of the page. And so that motivates us to try to figure out this probability of SI greater than S that we came up with here. And we've got these upcrossing rates. We've got some formulas for that. And one particular case that's going to be useful for us, where we'll get an analytic solution, is when x of t is Gaussian. Right, so if x of t is a Gaussian process, and that's a situation where we can face a lot. So we could think about, for example, let's say assume x of t is a single degree of freedom response. Say to Gaussian white noise, then we know that x of t was also Gaussian because it's this linear response. And if this SDOF has a natural frequency omega 0, we came up with an upcrossing rate for x that gave this formula below, omega 0 over 2 pi e to the minus x squared over sigma x squared. And I guess this is also for a zero mean process. Let's just say for mu x equals 0. So that's why there's no kind of mu up in this numerator term. Okay, so if that's the rate of upcrossings of any particular value of x, we can just use this formula in the numerator and the denominator. So this whole thing goes in, if I look at the cumulative distribution for SI, it was 1 minus the probability of SI being greater than some value small s, which was the rate of upcrossings. The rate of upcrossings of x is just a direct substitution of that. And then this denominator term, we'll use that same formula from above. It'll be omega 0 over 2 pi e to the minus 0, because x is 0 for the 0 mean. And so that term goes to 1. We're just left with the omega 0 over 2 pi. That'll cancel the omega 0 over 2 pi in the numerator. So we're left with just 1 minus e to the minus x squared over 2 sigma x squared. Okay, so we've got a closed form solution for this cumulative distribution function for SI. And we got to this formula using the kind of rates of upcrossings to figure out how likely it is that a particular cycle of loading is going to exceed some amplitude S. Ooh, and I've got a little bit of a notational hiccup back and forth here. So let's substitute this in a little bit. So S and X are equivalent in this case. So S is the threshold we're interested in. So let's make this the rate of upcrossings of S here. And so the only thing we have to do is plug in an S in the numerator, and then sigma squared on X. That's the variance of X, the stochastic process. Okay, and so this is going to be true for also for X greater than or equal to 0, because we assumed kind of positive. Right. S greater than or equal to 0, we assumed kind of positive amplitude crossings were what was interesting to us. And this formula is actually, might be familiar to you. That cumulative distribution function with the e to the minus s squared is the Rayleigh distribution. Okay, so what we can say kind of out of all this is that therefore the maxima of the Gaussian process with 0 mean, these maxima have a Rayleigh distribution. So we've got a closed form answer for kind of the CDF. And that Rayleigh distribution arose previously for some of you. So you can see in CE 203, we kind of bumped into the Rayleigh distribution in a somewhat similar circumstance. Homework number 2 related to wave heights. And the maximum heights kind of have this Rayleigh distribution for kind of related reasons to what we derived here. Okay, so now we've got a CDF for SI. And on the previous slide, I had said, okay, well, if we have the CDF for SI, that's this term here, we just came up with a formula for it. We could take a derivative to get to the PDF. Then we could plug that PDF into the expectation formula to get this expected value of SI to the B. So I'll save you the numerical steps. There's a couple little bit complicated steps in there, but hopefully you can see the path through these formulas to get to an expected value of SI to the B. And in this particular case, with the Rayleigh distribution on those peaks, we can get to a closed form solution for this expected value. And that's what's on slide 11 here. So when we've got that situation from the previous slide, the expected value of SI to the B is going to be related to the standard deviation of X, and it's going to be related to that exponent B, both kind of the exponent on this sigma X term, and then we've got a B over 2 factorial as well. Okay, so let's make a couple comments on this. So this was all true if we had the kind of so we've got Gaussian loading, and then we want to, so a Gaussian response, let's see here. Let's call this actually a Gaussian response assumption. It's really the response that's governing this formula. So Gaussian response is going to come from kind of a linear system with Gaussian excitation. And so that's a situation that arises kind of reasonably often. So we could think about, so I think about things like bridge girders having stresses in them under linear response under traffic crossing across the bridge. So if that traffic had some sort of a Gaussian excitation behavior to it, then this would all be fine. There are some circumstances where this isn't quite correct. So we could think about, let's say, if the response is a nonlinear function, in particular a nonlinear hardening function, of the applied load. So this would be a case where the response is kind of increasing disproportionately to the load. And so that's, so as an example, we could think about wind loading. So this would be if our response x of t was equal to some, so for wind, the forces are going to be related to some constant times the velocity of the wind squared. So if the velocity of the wind was a Gaussian process, then the forces would be kind of a nonlinear function of that wind. And because of that, our peaks, the peak forces could get kind of exaggerated, where and so what we'll end up with is kind of a heavier tail on SI. It's kind of more likely to get kind of very large amplitude SIs relative to this, the Gaussian response assumption. So then what we could say is that the expected value of SI to the B is going to be bigger than the Rayleigh result. Because those occasional large SI values, when multiplied by a B, or when raised to a B exponent that's greater than 1, we're going to get a very large accumulation of damage on some of those heavy tile cycles. So we've at least got a bounding result here. And we would say, okay, well, we know that the expected accumulation per cycle is going to be larger than this for those nonlinear cases. Conversely, we can say if the response is a softening nonlinear function, let's say nonlinear nonlinear softening function. So so that can happen kind of e.g. with structural softening under damage. So here I'm thinking about kind of pushover curves, say for a building under earthquake loads, where as damage starts to accumulate, the stiffness of the system gets reduced. So then the forces in the system will be lower at the extreme upper level relative to a linear system. And so in a situation like that, we're going to get the expected value of damage accumulation per cycle. It's going to be less than this Rayleigh result, because we won't have those heavy tails of high stresses as frequently as the Rayleigh distribution would say. So we're going to focus here on this Gaussian response assumption and use that one. That's a very frequently used, but just some notes here at the bottom of the slides to indicate kind of the relative impact if we had some other type of structural behavior. Okay, so let's come back. Now we've got this expected damage accumulation per cycle. We can kind of try to put this all together. So we can say the time to failure was going to equal the number of cycles to failure divided by the rate of cycles. And so we've got kind of delta being our kind of budget for damage accumulation. We've got the rate of cycles, and then we've got C SI to the B as kind of the amount of damage accumulated per each cycle. Right? So we've got kind of SI, the amplitude of cycle I, we've got, generally speaking, we could talk about delta as being a random variable, kind of how much damage we could actually accumulate before we get to a failure. And C we'll sometimes think about as a random variable, kind of the rate of accumulation, dependent on this kind of S out of the B, damage accumulation per cycle. So those could all be random variables. And if that's the case, then TF is going to be a random variable, obviously a function of other random variables. So what we'll think about generally is the time, and we can think about kind of a probability density function for TF. So we'll end up with some sort of PDF. Probably looks something like that. And we can compute, say, an expected value of TF, and we kind of have the ingredients to get at that approximately, at least, because we know some expected values of these other coefficients. But we're generally not going to count on this expected value of the time to failure. We'll generally say, well, I'm only going to count for some level of design life that's over here, where I've got a relatively small probability that I'm not going to make it to that amount of time. And so the question is, how do I figure out that design life and pick that? Right. So if T design is my goal, right, I've got a couple ways that I can compute this thing. So my first option would be to calculate the expected value of TF. Okay. And we kind of know the pieces to calculate that thing. And then in terms of my SN curve that I'm going to use for my design ultimately, then we could make an adjustment. So if we had kind of the real C and B that we thought were appropriate for our particular material or our particular situation, we would adjust those, and then we would say the number of cycles that we can handle under kind of our design condition. That's going to be a little conservative. We'll call that kind of 1 over C tilde Si to the B tilde, or C tilde and B tilde are some adjusted coefficients that'll give us some kind of conservative design life. Okay. Another way we can get at this is to say, let's go gather some empirical data. So I have kind of the log of the number of cycles to failure and the log of S, and here we're going to take kind of an average S in some sense that's going to take into account kind of the variable amplitude loading, and we'll do some experiments. And because our characterization of kind of damage per cycle is imperfect and our material behavior is kind of imperfect, it'll depend on it'll vary from specimen to specimen, even if we have a kind of nominally identical specimens. So we'll get some kind of experiments out here, and then what we might do is we might pick a line that's kind of below those experiments. So we're going to assume kind of a lower number of cycles to failure than we actually saw in the experiments. Let's make a little legend here. So the dots would be experiments, and the line would be the design equation. Which is going to underestimate NF relative to what we saw in our experiments. Right. So in this type of approach, we might just choose C tilde and B tilde kind of directly off of data like this to conservatively predict the experimental results. Okay, so this approach actually wouldn't really rely on all that math that we just did in the previous few slides. We could just throw up some experiments and put this design equation on here. but so in some sense that kind of shortcuts the mathematical complexities. But I think having some underlying sense of the mathematics kind of more related to the option one, where we could actually compute this stuff directly and then make a conservative adjustment. That one's a little bit more transparent in terms of what the ingredients might be to go into one of these types of models. Okay, so maybe actually let's just try to summarize what we went through here. So we took our random vibrations models, and particularly those crossing rates models, and we used those to try to move to a model for fatigue failure. And so the fatigue failure model we explored here is the one, it's Miner's rule. This is kind of the most popular and simplest model here. And the idea is that we're accumulating damage over each cycle of loading. And so the amount of damage within a cycle is going to depend on the peak stress within that cycle. So at each cycle, which is a upcrossing of the mean, we need to know what the peak stress is. And then we can raise that stress to an exponent b to indicate damage. And then we're going to add up that damage over all the different cycles to figure out how many cycles we could sustain without seeing a failure. And so the number of cycles to failure is a random variable, but we can take expected values to try to get to average numbers of cycles and expected values of time to failure. And the analytical solution that we can get out of all of this is the case where the response and those stresses are a Gaussian process, because in that case we had nice closed form solutions for the rate of upcrossings, which we could use to get at a probability distribution of those peak stresses. And we saw that the peak stresses are going to have a Rayleigh distribution. So each cycle, the peak stress is going to come from this Rayleigh distribution PDF. And we can use that to get to the expected value of damage per cycle, which was that stress raised to the power b. And then we can put that all back together and get to an expected numbers of cycles to failure. So we've got kind of nice closed form solutions there. Those form the basis for things like simple design rules. In other situations where there's some nonlinearity, you can get a bound on your answer, and so that's still relatively informative. Ultimately, since these things are all empirically calibrated, even if the theory doesn't perfectly match up with the circumstances it's being applied to, we can make up for that in some kind of empirical calibration of the coefficients for the model, and it still motivates the functional forms of these models, and those functional forms seem to be quite robust in a lot of circumstances. So it gives us some confidence that we understand a little bit what's going on, albeit with some assumptions, but it seems to be a reasonable model for the world under these high cycle fatigue cases. Okay, so hopefully that was a useful exposure to these fatigue failure models and kind of what some of the assumptions are underneath of it, and hopefully that was also a useful way to see application areas in which these upcrossing rates can be used for various types of calculations. So that'll conclude section 12. Thank you.